All right, hello, hello. Good morning, afternoon, evening, middle of the night, wherever you are in the world. Happy Monday, Tuesday, wherever you are when you're watching this. I'm Alexander. I am the head facilitator for this IBM data science class. Hopefully, you've seen me in some of the posts and videos floating around the forums over the last few weeks. And welcome to week 5. So, after this week, we'll be officially halfway done. I got a bit excited yesterday because I was doing the math and I'm like, wait, are we halfway done yet? Not quite. But I think we're basically halfway done with content, which is really exciting. So for those of y'all looking ahead, right, where we've come from, where we're going, week 1, thinking like a data scientist. Week 2, thinking like a computer programmer. Week 3, data acquisition and data formats, basically getting data into your system. Hopefully my screen is still being shared. Week 4, all about SQL, databases, data engineering. And then week 5 is going to be more of our introduction to modeling, specifically linear modeling, data visualizations next week, and then 2 weeks of machine learning, and then 2 weeks of capstone, and then we're done. So we're flying through this. Let's see, a couple logistics. Not too much on the logistics side. For week 5, it's a lot of coding concepts and a lot of interactive labs. Unlike week 4, which was split into what I called kind of your click-through labs or your just more interactive type of pre-run labs for SQL, week 5 has a lot of Python code for you to write. So we won't be going through all of them today. But I will be hitting 5.3, 5.6, and 5.10. 5.10 is the big project of the week, where we kind of synthesize everything together. Should be fun. I think other logistics stuff, make sure to participate in the forums if you have not already done so, or at least monitor them. We at least get a track like how many clicks and views these all get. So try and participate as much as you can. We got 4 topics for week 5. Again, you don't have to participate in every single one of them, but at least try and read over them and try and reply back if you can. Be aware of the live session threads and the lounges. This is kind of where Karen and I will be posting stuff. For example, I posted some things about our week 4 recap and kind of expectations kind of for today in the live session thread. And in the lounge, you'll see a bunch of fun topics that Karen has brought up around kind of different data types and feature engineering and feature types and null values, all of that good stuff. So a lot of good stuff in the lounge over the last couple weeks. And if you're not all the way caught up with Module 5, don't worry. I know there's a few folks still working or actively working and participating in the week 4 stuff, and that's totally fine as well. I think the only caveat I have is that technically you have to be all the way wrapped up with the end of Module 10 by 1 week after kind of my last week or our last live session or last week. So you have about like 5 to 7 days to get everything kind of squared away to be officially graduated. Remember, all that's graded each module is the final assessment quiz, but I highly recommend you also do the final project you have at the end of each module. So for module 4, that was what we did in our last live session. We analyzed crime data in Chicago and census data in Chicago. For this one, we're going to be building models, I think, on housing data, which would be a good time. But again, those aren't graded technically. And same thing with the forums. They're not technically graded either, but uh, is only here to help facilitate your learning. All right, let's just dive into things. First, big ideas for Module 5. Not only are we going to talk about a little bit of pandas and how we can interact and kind of massage data, we're going to do a soft introduction to what I call linear modeling. Linear modeling uses mathematical algorithms to create predictive models. So complicated way of saying your line of best fit, your rise over run, your slope, right? Just drawing your straight line for linear regression. So we're going to talk about linear regression, multivariate regression, or multiple linear regression, and finally polynomial regression, which is kind of a more advanced way of fitting polynomial curves to your data and not just straight linear relationships. I'll give you a little bit of history on that, and then this is our introduction to machine learning, as your foundational machine learning models are actually linear models. All right, but before we get into that, let's start with some data wrangling. So I mentioned I'm going to do a couple of different labs here to start. I'm going to try and be done in 60 minutes or less to leave 15, 20 minutes for general questions or office hours. So let's just dive into it. Let's see. Karen will be managing the chat. If you have any questions, I'll also be checking in on the chat and any if you do have any updates there as well. All right. So I'm gonna start with with 5.3, just because I really like how this media set kind of introduces data preparation, right? And I think last week or the week before, I brought up the idea of garbage in, garbage out. You could build the best model in the world, but if it's trained on bad data, you're going to get bad responses. You see this in the real world with RAG chatbots. That's your kind of AI, LLM driven chat interfaces. If they have bad data that they are referencing, they're going to give you bad answers. So some people blame the LLM for doing the hallucinations, but in reality, a lot of the time is the fact that the data given to the LLM is incorrect or fake news, fake data, etc. And that's what causes the LLM to hallucinate. So same idea in general predictive modeling like we do, or statistical modeling that we're going to be introducing today. If you have bad data, you are going to create bad models. And this is actually brought up in a couple of the sessions in Module 5. As I can find one. I think it's Module 5.8. We're not going to do the 5.8 um, notebook today, but I did them all already. They're in my GitHub, so you can feel free to reference those. But the laptop models, you'll see the laptop model is actually really bad. And it's like the data that goes into this model is just not really relevant to trying to predict your CPU usage or whatever it's trying to do. So again, don't always blame the model. If your data is bad, no matter how fancy or how complicated you make your model, the model won't be that good. So pre-processing is the idea of cleaning your data and getting it ready for modeling, right? How do we wrangle, massage, engineer, pre-process our data to make it usable for models to identify patterns? So again, that's all that a predictive model really is. It identifies patterns in its training set and uses those patterns to predict a test set or an unseen future state. So let me pull up the notebook. Again, I recommend watching the videos and kind of reading over all the notes on your own time. And let's get started with some of our activities. I'm going to do the second activity. The first activity is a introduction to the idea. The second activity is the more hands-on lab here. And remember, these labs will be run in your Jupyter lab environment. And so hopefully this should all just work. Yeah, and they give you the solutions too if you need them. All right, so let's hope this works. We're gonna connect to our kernel, restart and clear output. Wait for that to click over. Boom, I think that worked, hopefully. And now let's see if this runs. Sweet. All right. So first thing what we're gonna do with this lab, we're just gonna be a soft introduction to data wrangling. And if I go fast, I'm trying to get through 3 notebooks in an hour. So again, take as much time as you need on these on your own time. And again, I do recommend kind of running these notebooks and reading them on your own as well. So first thing we're gonna do is fetch our data. In this case, we're going to be acquiring this laptop's CSV, and it's going to be this laptop's data that we're then going to start cleaning. So if I open this up, you can see what the CSV kind of looks like, right? We have a weird column here that's probably some index that doesn't even have a column name. As we kind of scroll across, we can see we have other features that look to be pretty good. The size of the screen, the CPU, the price of the laptop, how many GPUs it has. So yeah, this is kind of what a quick preview of what this data is that we've downloaded. But as we'll see, this data is not beautiful. There's a cool function in pandas called df.info. df.info gives us information about the data types and null values. So I'm looking at this .info, which is giving me, again, that information about the data frame. And I'm looking for two things when I look at the I guess three things when I look at the .info. The first is going to be the columns or the column names. Is there anything kind of weird in the column names that I should be flagging? Do I need to kind of standardize them, lowercase them, fix any weird values? Sometimes there's like weird white space in your column names, or foreign characters like percent signs and stuff that can throw off pandas. So in this case here, I see this unnamed 0. So that's kind of a weird column name, right? And as we'll see, that's that irrelevant index column that we got loaded up in our data frame. The second thing that I look at is the null values. So this is kind of confusing because what it gives us is the not null count. So what you're looking for is any of these that are not the number of rows in the table. So in my data here, we have 238 rows, right? So what this is saying is I have 238 not null manufacturers, which is good. That means we have 0 null values, right? We have 238 not null of 238 rows, so we have 0 null values. Contrast that to screen size. Screen size has 234 not null values. So womp womp, this means that we have 4 null values. And so that means we need to fix it. As we've talked about, linear models, predictive models, they try to identify patterns to predict the future. So if we have a null value, it's pretty difficult for models to find patterns in that, especially numeric patterns, right? So we have to deal with some null values for screen size. And then finally, the third thing I look at is the data type, right? Typically, especially with linear models, we need our data to be numeric. So I want to make sure that all my data is the correct data type and preferably numeric. And I see one column screen that is a string. Oh, same with manufacturer. This is also a string. So we'll deal with categories here in a little bit. Karen also had a great post in the lounge about how to deal with categorical or string-based data. And again, remember when I talk about categories is basically like red, yellow, green, or A, B, C. It's a group or a text group that multiple rows can belong to. Contrast that to like a full text column, which could be something like a product review, right? A product review is not a category because it could be a paragraph of text that is unique to that specific row. A category is basically a group or a group label. So we can see both manufacturer and screen are both categorical features here in that they seem to be groups that multiple rows can belong to. So we'll have to deal with that at some point down the line. So my .info is giving me a lot of information already, right? Without even doing any other code, I have an irrelevant column that we need to drop. I have null values in screen size that we need to fix, either drop or impute or fill in. And then we have 2 string-based features that we've confirmed are categorical that we have to somehow turn into numeric features. This is going to be called encoding, which is kind of fun. All right, so long story short, the df.info is one of the most powerful functions in pandas, especially as a data scientist. So use it, actually look at it, and try to interpret its output in a meaningful way. All right, so let's kind of get to work here. Let's look at the first 5 rows, and then we can see that screen size is this weird decimal number. This is a little bit excessive. So all we're going to be doing is rounding this to 2 decimal places instead of 3. And we should see that, yep, now we've rounded our decimals. So we still haven't fixed our data, right? We still have a few things that we need to do. Null values, imputation, and then we're going to fix some data types, and then we're going to do some standardization, normalization, binning, and categorical variables. So I think a few of these are actually not fully correct. For example, it's telling me here that weight, kilogram, and screen size are strings, which I don't think they are in this example. But we'll still run it through it just for completeness. All right, first thing we're going to do is we're going to look at the number of null values. So this code basically does the same thing that .info does, except instead of counting not null, it's going to count null, right? So we're going to go through and we're going to print out the number of null rows. Again, this is kind of excessive, but basically you can see what it's doing is that it's counting the number of trues where is null is going to be where true, basically. So we can see that we have 4 null values in screen size. That's the only column that has null values. Again, there's a lot of, I guess weight kilogram also has 5 null values. I didn't realize that. Oh yeah, there you go. Weight kilogram has 5 null values as well. Cool. So when you have null values, you have 2 options. Your first option is to drop the row. This has some pros and cons, right? Dropping a row means not only do we just drop that row for the null weight, but we also drop all the other information in that row, right? So I like to do, let me actually write some custom code here. Oh God, writing live code. df.locate where df.weight kilogram is null. Let's see if that works. Ooh, great. So these are the 5 rows where weight kilogram is null. So if I just drop these rows, the con is that I lose any meaning, right? I lose any predictive power that these other features may have in identifying a pattern. Let's say we're trying to predict price, right? Maybe there's some reinforcement pattern that we can add with the screen size or the GPUs here and how they correlate to price. We would lose that information if we just drop these whole rows. So that's typically a con, right? You lose some of the data power by dropping rows. But the pro is that it's easy. It's super easy to just delete rows. So sometimes I do that as in my own work. A common heuristic is if you're going to be dropping more than like 5 to 10% of your entire rows, then you should probably impute them and not drop them. But if you're only going to be dropping less than 5% or less than 10%, then it's probably fine to just delete the rows. So in our case here, we have 5 rows out of 238. We can do some quick math on that and say that this is actually only going to be 2% of my total population. But actually, if we include the 4 null screens, we're going to be dropping 9 rows, which is about 4%. So in my work, you could probably drop them. It's probably fine. But in our idea here, we're actually going to impute. So that's one of your keywords of the day, IMPUTE. Essentially, it means fill in. We're going to replace the null values with a real value. So in our case here, we're going to be filling them in with the average of the rest of the weight kilogram column. So we can actually look at what this looks like. Let me plop this in here. And I'm just going to print that value. So we can see that the average weight in kilograms of my laptop is 1.86 pounds. So now what we've done here is that we have filled in our 5 rows. We have imputed those 5 rows with the average 1.862. This is fine. You may want to check the distribution. Sometimes you want to use the median instead of the mean for your imputation. And of course, another one is the mode. So the mode is typically what's used the most for categorical values. And it looks like that's what we're going to do here. For screen size, I'm actually going to run this a little bit separately. So I'm going to comment this out. So let's print the most common screen size. So remember, the mode is the most frequent value. What's the value that shows up the most? So in our case, the value that shows up the most for our laptops is 39.62. But if we just take the mean, and again, we can fill that in with this line right here. We can see that the average laptop screen size is 37.26. And if you really wanted to be crazy, we can also see that the median is 38.1. What? So we have three different values that we could use here to fill in the null screen size. And again, there's no right or wrong answer. Typically, I would look at this and say, all right, I would probably go to the median just because we have some skew in our distribution. Um, but we'll get to that later. But the mode also works. Long story short, there's multiple ways to impute your data, the most common being the mean, median, and mode. And you, as the data scientist, need to make that decision and justify it. And sometimes, especially if you have a lot of null values, you can try different ones and then see how your model reacts to kind of different imputation strategies. All right, we've gone over imputation. Let's go over fixing data types. Again, this is not really the case here since these are already floats anyway, but we can fill those in with a float. So now if I do my df.info, we should hopefully have 0 null values. Yep, we filled in all of our null values and we fixed the data types for at least these two. All right. Last thing we're going to do is do some data standardization. This typically is with units. So if we look at my data, let me pull my data back up. I was going to say, you may have heard the joke that 90% of a data scientist's time is data cleaning, and that is the truth. So looking at our data here, what we're standardizing in is we have centimeters and kilograms, and basically we're going to convert that to what is the American version called? Imperial versus metric. Yeah, so we're going to convert it to the imperial system. I guess because USA. Um, cool. So we're going to standardize and change our units here. So again, I'm just stealing this code. Typically, I've used this when I have some features that are in like feet and inches, and then some are in like centimeters. Typically, you want to standardize across like one unit of measure system. All right, and then finally, we're going to look at normalization. Normalization wasn't discussed that much in the media sets, but it's a really powerful technique that we're going to touch more on in weeks 7 and 8. Basically, the idea here is if I look at CPU frequency, actually, I guess this isn't like that crazy. I wouldn't probably normalize this feature, but I guess we'll do it for example. So the reason why we would use a normalization strategy is when our features vary a lot. So let me see if I can find one. Let me do a df.describe. df.describe gives us our summary statistics for each of our features. So typically what I look at for normalization is when my minimum and my maximum have a very large difference. So maybe we can see the storage in gigabytes, right? We go, actually not really, 128 to 256 isn't that big of a change. So none of these features are really that skewed, so I probably wouldn't need to normalize any of these. But I guess for the sake of the example, we're going to normalize CPU frequency. So CPU frequency, we can see that the frequency goes from a minimum of 1.2 to a maximum of 2.9. So I guess a better example would be something like, I don't know, distance to your nearest fast food McDonald's, right? Maybe for most of us, it's like a mile, 2 miles, 3 miles, but maybe some of us live in a country or a city or a rural area where the nearest McDonald's is 300 miles away, right? So in that case, my feature varies, has a high variance, right? It goes from 1 mile, 2 miles, all the way up to like 500 miles. When you have a feature with high variance like that, sometimes it can cause confusion in your models, right? Your models may be biased towards a bigger number, and they may think that number may have like a bigger impact. So what normalization does is that it standardizes our data set within a range, usually a 0 to 1 or a -5 to 5 range, depending on if you use a max-min normalizer, which is what we're doing here, versus a z-score or a z-score type of normalizer. So again, we'll talk more about normalization when we get into the machine learning units in week 7. What I wanted to do here now, if I run my df.describe after we've done my normalization, you'll see that my CPU frequency is standardized between 0 and 1. Great. So the idea here is now my model won't get biased or confused by any excessively large numbers in the feature set. All right, we'll fly through these last couple here. What these last couple ideas are doing is feature engineering. We're creating new features, new columns from our existing feature set. So the first is going to be looking at price. Obviously, we have a continuous numeric variable for price, but what if we wanted to build a like categorical model? We wanted to predict the likelihood of being a category of low, medium, or high. To do that, we can use binning. What binning does, it takes a numeric variable and it turns it into a category. So a common example for this is like age range or age group, right? We all have a continuous numeric age value, 18, 19, 51, 57, 65. But typically when we use age as a feature, we use age groups. 18 to 25, 25 to 39, 40 to 50, 50 to 65, 65 plus, right? Those are groups or categories that we can define by binning our numeric data into that. So let's run that, and then we can create a pretty little bar chart to see what it looks like. And we can see that most of our laptops actually fall into the low price bin, which is kind of interesting. Other use cases for binning may include things like categories that have very excessive like distributions. So what I mean by that is, let's say you have a category that's called like country in the world where you're from, right? And we find that a majority of people like taking this class are from the United States, China, Japan, India, Germany, England, Spain, Portugal, right? And then we also have like one, two, three others that are maybe from like Tonga or Indonesia or South Africa or something, right? But there's very few of them. Sometimes it can be worth binning those other countries into a category called other or miscellaneous, right? So that can also help decrease the noise in your predictive model. And finally, the last thing that we're going to do is deal with our categories. So what we're doing here is we're transforming our categorical variable of screen into dummy variables or indicator variables. Typically, these are going to also be known as your Boolean variables. We're converting the screen into a 0 and 1 column. So let's see what that looks like. I don't know why we need to print that. Here's kind of what this looks like. You'll notice that we have, oh, I need to do sure, you can do the true false, but I recommend also converting that to an integer. This is like a new thing that happened in the get dummies function in pandas. D type equals int. That's what I needed. And now I have to rerun my whole notebook. So give that a second to run. The reason why I have to rerun the whole notebook there is because we drop the screen column here. So I can't rerun this cell because it'll throw an error that the screen column doesn't exist. Let's see if that works. Oh, we're still reconnecting to the kernel. I guess we'll just run them manually. Boom, 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 boom. All right, cool. So there we go. We can see that we have zeros and ones that represent our binary columns here, right? We've turned this categorical column into a numeric column just by running those zeros and ones on it. Note we can actually do this with our other one. So let me see if I can do that live here. We can do. I'm just gonna run it. Oh my God, what are we doing? There we go. Let's just run this on manufacturer. If we run this, we can see that we can turn this categorical column of manufacturers into this sparse matrix. Ooh, fun words. Sparse matrix of zeros and ones, right? Where now, if the row belongs to a specific manufacturer, we'll have a one for that row, right? And this is something that models can interpret better than strings, right? Almost all models, as we'll talk about them, require numeric inputs to be able to identify those patterns. So this is why we do this. So I really think that the first like three media sets are very important. And again, the reason why data wrangling, data preprocessing, feature engineering, all similar terms for the same idea. How do we clean and prepare our data for use in a model, right? How do we make sure that a model can generate the most, can identify the most pattern, the most signal in our data, as well as kind of get more fun and in the weeds with specific pandas functions. You'll notice that everything we did in this notebook utilized pandas and NumPy, which is kind of why we introduced that back in week 3 or 2, whatever it was. Cool. Again, feel free to drop questions or thoughts in the chat. Yeah, age groups are good for binning. Other ones, what's some other ones I've seen are like years, right? Sometimes it can be really obnoxious to have. Let's say you have a feature for like the year that a house was built. Maybe it's like 1956, 1981, 2021, whatever. Sometimes it's more predictive to bin those into decades, right? So is the house built in the 50s, the 60s, the 80s, the 2000s, the 2020s, and having that as a categorical feature that we can then encode using, this is called one-hot encoding, by the way, which again, we'll introduce in more detail in week 7. We can take those categories and then turn them into binary features like this. And sometimes that is more predictive than just having the noise of a house built in 1951 or 1957. And again, think about it. That's all that a model is trying to do, identify signal and patterns in data. So if you give it too much or too much like nonsense, is there really that big of a difference in using a house and saying that a house was built in 1952 versus 1958? And is that really going to drive a difference in price? Probably not. But saying a house was built in the 1950s versus the 1980s, that is probably going to have more of a pattern, right, in how that price of that house is decided. So that's what we want to do. We want to strengthen the signal in our data using these pre-processing techniques. So binning, normalization, imputation, right? All of that is really good first steps into cleaning and preparing your data. All right, I'm going to jump into the next notebook I wanted to go over, which is going to be our 5-6 notebook, Introduction to Modeling. And then we're going to tie those ideas together kind of with the some of the other ones. Again, you have media set, you have notebooks for a whole bunch of these, 5.3, 5.5, 5.6, 5.8. So I recommend you do all of them. 5.5 is more like distributions, looking at visualizations, looking at kind of what do I mean when I say skew, right? So that's what 5.5 is all about. You can look at like your box plots, right? What outliers do we have? What's kind of the distribution of some of our features, etc. So that's a good one to review. And then 5.8 goes into model evaluation, which we'll incorporate here into 5.10 as well. Again, now with why they only want me to do 5.10, but let's jump into 5.6. All right, so we've talked a lot about how we're preparing data for modeling. So what is modeling? What are we trying to do with a model? So in this media set in 5.6, it introduces the concept of linear modeling. Linear modeling is the very first step into predictive modeling that we've ever done. So just a quick history. Predictive modeling, especially with linear modeling, goes back hundreds of years, right? You remember like Isaac Newton with his calculus and Galileo looking at planets. All of that used linear modeling to define kind of those characteristics. So the big idea with linear modeling is that it's rooted in pure mathematics, right? And what I mean by pure mathematics or pure statistics is that we can write an equation to define how our model works, right? There's also mathematical proofs that exist to give us confidence in the equation that we end up with, right? So for example, we're going to start here with linear regression, right? Linear regression is one of the, I guess, very introductory kind of algorithms for doing linear modeling. You're going to notice we're going to be using a library called scikit-learn. Scikit-learn is one of my favorite libraries in Python. It's a one-stop shop for anything that you want to do. And again, we'll get deeper into some of these in week 7. So we'll start with kind of linear modeling in regression. You can see it's the very first one, right? Within linear models, ordinary least squares is going to be our linear regression model, right? This is where we start the journey into predictive modeling. So what we're going to do with linear regression, right? It's going to be first identified with the proof of ordinary least squares. So you may also hear this as like OLS regression or OLS proof. So the proof of least squares is actually very fun. Let me see if I can find it. It's like it's like the MLE for least squares, right? Maximum likelihood estimation. Yeah, God. Sending me back to undergrad. I had to like write all these proofs out in little blue books because it was all pre-AI and everything. It's a whole thing. Anyway, there's a mathematical proof to what a line of best fit is, right? So what we're gonna see is when we run a linear regression, right, we end up with a line, right? Let me see if I can zoom in here. Boop, boop, boop. So we have a line, and this is known as your line of best fit. The reason why it's the line of best fit is because it actually minimizes the distance from every point to the line, right? If we look at where we draw the line, there's only one line you can draw in this data that minimizes the total sum of error or the total sum of the distance from all the points to the line. That error is known as the residual, residul. That's another vocab word I'll type out. But yeah, long story short, there's only one line that minimizes that distance. If I draw another line like this one, kind of by mathematical proof, this line that I drew is not the line of best fit because it does not minimize the amount of total error or the amount of total distance from my points to my line. So long story short, that line of best fit is defined via a mathematical proof for least squares. And this also transcends dimensionality, right? We all love this about math. And again, you don't have to go too deep in the weeds here. But in a regular kind of two-dimensional set like this, we have a flat line. But if you think about it, gets your head exploding a little bit, you can have 7 dimensions and you can draw a line in 7 dimensions. You can draw a straight line in 7 dimensions. In mathematical theory, you can draw a straight line in like n dimensions. So that's going to equate to our number of features. If you think back to our laptop problem, and what we're going to see here is if I have 5 features to predict the price, right, to predict our target, when we draw our line of best fit, we're drawing our line in 5-dimensional space or 6-dimensional space, which is kind of funky to wrap your head around. But big idea with linear models, and starting with linear regression. Linear models are defined in mathematics. They all have an equation, and they're all rooted in mathematical proofs and theorems that only result in one right answer, right? There's only one line of best fit. Karen can come up with a model, I can come up with a model, and it'll be the exact same model, right? Because there's only one answer. And again, that's kind of the beauty of mathematics for this. So that's where we're going to start, right, with modeling. We're going to start with linear models. And again, back in the day, people were solving these with pen and paper, right? Galileo did not have ChatGPT to do it for him. So with linear modeling, the idea is that they're they're really explainable, right? It's pretty easy to explain to a non-technical stakeholder what your line of best fit is doing. We've all kind of seen this since Algebra 1. You have an equation, the equation's really explainable, right? So in my experience in baseball, we used a lot of linear models because they were more explainable to coaches and players and non-technical people about why our prediction is what it was, right? So you'll see this with a lot of different industries. When we start moving into tree-based models and then neural networks and things like that, the explainability level really trails off, right? You might hear some of those other complicated models be thought of as black box algorithms. And we'll get to that in about 2 weeks. But linear models are a great way to start, and then combining linear models with polynomial regression, which is the same big idea as linear models, but instead of doing y equals mx plus b, we're going to use y equals mx squared or y equals mx cubed, right? We're going to start using polynomial features in our set. In summary, only thing you need to know. Predictive modeling starts, and it's been around for hundreds of years. Typically, linear modeling, neural network, or a tree-based model. What are you doing? Why would you ever use a neural network when a linear regression can do the job, right? So that's kind of the idea. And the reason why we like linear models, they're very explainable and they're very easy for computers to deal with, right? If Galileo was doing them with pen and paper, quill and ink and papyri, I don't know, then a computer can solve a linear regression in like milliseconds. It's great. Contrast that to like a neural network, which sometimes can take your computer's days or weeks and maybe require specific hardware like GPUs and TPUs, hence NVIDIA's stock going to the roof. And you do see this a lot with new data scientists. People just go straight to a neural network when they don't even test out a linear regression, and half the time a linear regression will do the job just as well. All right, so let's look at what our data looks like. We have that same data, data from earlier about our laptops. Note we still have a couple of bad columns here, but for the most part, this looks pretty good. All right, so what we're going to do here is that we're going to use the CPU frequency to try and predict the price of my laptop. So my feature is CPU frequency and my target is price. And to do that, we're just going to do a quick basic linear regression. Note this is a one-dimension linear regression, right? We only have one feature, CPU frequency. So this is your ordinary least squares. And then from there, we can look at the output of the model using Seaborn. And we can see it looks something like this. So what we're looking at here is that the red line is the actual price of my laptop, and the blue is the predicted price. So we're pretty close, but we also have this weird spike here where it seems that we are under projecting the price, right? The price probably goes up to 3,000, 4,000, and we're probably projecting them at around like 1,800. So this is another problem you'll see in data science, which is sample size. I'm looking at this distribution plot and I'm seeing that we don't have very many laptops that are priced above 2,500, right? And if the idea of predictive modeling is pattern and signal, there's probably not enough rows or examples here to trigger a confident pattern of what actually predicts laptops that high, right? So you see this also with housing prices. If you go look in your neighborhood, most of your houses are going to be like $500,000, and maybe you have a handful that are a million, 1.5 million, whatever, right? And it's really hard to build a model to predict those expensive houses because it may only see a handful of them in a data set of thousands of houses, right? So similar idea here. We have very small number of examples of expensive laptops, and our model doesn't do a great job of predicting those expensive laptops. We can see how good our model is by looking at metrics. Metrics that we use for modeling include R squared and mean squared error. I'm also partial to mean absolute error, MAE, and we can get into all those in the kind of forums as well. But essentially what R squared and mean squared error, what all these metrics are trying to do for a regression problem like this, it basically looks at the amount of error in your data set, right? So remember our little talk about residuals and stuff earlier. Every metric for regression problems is based on that residual, right? So if I look at my error, R squared essentially just measures like how far away or the kind of the spread of all of my points around the line, right? Are they pretty spread out? Are they pretty narrow, right? If all my points are very close to the line, then my R squared value is going to be low. In a vacuum, R squared is a pretty good one-off metric to look at. However, when we start testing multiple algorithms, R squared kind of loses that luster a little bit just because it's not very explainable. It doesn't provide any uncertainty intervals around your model. And if you have a lot of models that are close in R squared, you kind of need something else to really tell you which is the better model. So enter mean squared error, which is exactly what it sounds like. It takes your residuals, it squares them. So it takes that kind of puts them all in a positive range, whether it's a positive or negative error. And then it takes the average. So it gives you the average of the squared error. MSE is pretty good. It's a good metric. It's good in comparing models against each other. Where MSE kind of has some limitations is if you have like one really bad miss, right? Because we square the error, this one miss gets overly, I guess, emphasized in how bad your model is. Further, it gets us closer to an uncertainty interval. We could take the square root of the MSE. This is known as your root mean squared error, or RMSE, and we can use that square root value as a proxy for a confidence interval, right? This is my average amount of error that I have in my model. And then I like MAE. MAE is your mean absolute error, which does the exact same thing as MSE, but doesn't square the values. So this can more fairly balance out your errors, and it's already at the same scale as your data set. So you don't have to take the square root of it or anything. So MAE is good. MSE is good, and then R squared is okay, I guess. But yeah, problems with R squared is that it doesn't really give you any uncertainty in its value. And when you start having multiple models, it can start converging, and we really need something else to tell the difference. So R squared and MSE are great places to start. So again, let me actually do some live coding. Oh my God. np.squirt. Hopefully this works. Great. So what I've done here is the R squared is 0.1, which is really bad. This means that we're not very predictive. And my root mean squared error is 533. That means on average, our model is off by $500, which is not great when like some of our laptops only cost 1,000. So if I say that I predict this laptop will be $1,200 plus or minus 500, that doesn't give you a lot of confidence. Right, so I'm looking at this, I'm like, oh my God, we created a really bad model. Cool. Let's fly through some of these other ones, and then we need to get into the actual project. So beyond linear regression, right, we can do multivariate linear regression. Multivariate linear regression is exactly what it sounds like. We use multiple features. So this is where we go into n dimension space to predict our target. So in this case, we have 1, 2, 3, 4, 5, 6, 7 features. So we're going into the 7-dimension feature set, and we want to draw our line of best fit there. Or I guess technically 8 with the price. So we have this 8-dimension space, and we want to minimize our residuals with our line of best fit. So that's what we're doing here. And we can draw the same type of distribution plot. And ooh, we're actually a little bit closer. This looks pretty good. Again, maybe I should add in that legend. I don't know why they lost the legend here. Here is my image. We can see that red is the actual price, blue is the predicted. So it looks like we still over predict price a little bit, and then we under predict price above 2000. And again, I think that's all due to sample size down here, but we should hopefully get closer to the red line with some more tuning. If we look at our values, what we should see is that um, because our model distribution looks better, our metric should also be better. So hopefully this still works right. Oh yeah, here, this is where there was a typo in the solution. Find the R squared of the fit when did LM1 Y hat capital Y. There we go. Y hat. There we go. I think that's what we needed. And then this is LM1 dot score. What are you mad about? Yes. What else is my input here? Z, not X. Oh my God. Boom. So there's our value. We can see my R squared is shot all the way up to 0.51, which is mediocre, but it's good. That's better than 0.1. We can see that my mean squared error is lower and my root mean squared error is also lower. Now, if I tell you that we predict your laptop to be $1,000, it's plus or minus 400, which is better than 530, but still like not that great. So I still think I still wouldn't productionalize this model and like actually use this to sell laptops. But we can see that adding more features does improve the model, which is good, right? That's expected. And then finally, the last one here is the polynomial regression. So polynomial regression is pretty interesting. Again, what it does is that with linear regression, we fit the equation y equals mx plus b, or if you're super fancy, it's like they didn't give me it here. Let me do linear regression equation. It's actually going to be something like y equals b naught plus b1x. Oh yeah, here we go. Y equals b naught plus b1 x1 plus b2 x2 all the way blah 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 all the way down. When we start introducing polynomial regression, it's still the same 10,000 foot view big idea, right? It's still going to be fitting it's still going to be fitting an equation, and it's still going to be using mathematical proofs to fit it. But notice the polynomial equation down here at the bottom. Y equals b naught plus b1 x1 plus b2 x1 squared plus all the way along where we start raising these features to the value of n. And this allows us to fit curved equations, which allows us to capture in the industry what we call nonlinear effects. So feature interactions that are not defined by a straight line. We can use polynomial models to define that. And you'll see that when we start moving into more complicated algorithms, tree-based algorithms, things like that, they can capture nonlinear effects implicitly without needing all of these crazy polynomial features and stuff. When we get into polynomial regression, in my opinion, you start losing the benefits of linear regression, which is that explainability, right? It's a little bit more difficult to explain a polynomial curve to a non-technical stakeholder in terms of how it makes a prediction, right? So if we start losing, and we increase the complexity of the model as well, which can be kind of a pain. So a lot of interesting, different nuances as you start progressing through here. All right, let's kind of wrap up our function. Again, all we're doing in this step is we're just showing what a polynomial is. So again, what this is doing is that it's showing with our degree equals 1, we have a straight line. When we have a degree of 3, we start having a curve, right? I can't remember what the name of this is. It's not a quadratic. It's the one above a quadratic. And then when we have 5, we have an even curvier curve. Ooh, yay. So the idea is as you add in more degrees to your polynomial, you can capture more and more nonlinear effects. But the problem is that if you do that, you'll probably get a lot of overfitting, which is where we start tuning our model more to the data than we need to. So you can actually kind of see that here. This is saying how good is our model with just this one feature, with just CPU frequency, how good is our polynomial fit? And as we go from 1 degree to 2 degree to or third degree to a fifth degree, we get a better model, right? My R squared goes up each time, which indicates that we are fitting a better curve by adding in more of these polynomial features. So let's just tie this all together. What we're doing with this little pipeline is that we're doing some pre-processing. We're scaling our feature set. We're then introducing our polynomial curves, and then we're going to shove that all through a linear regression. And when we do this output, I actually want to do one other thing first. Let's look at the distribution of our predictions. Cool. So in this case, my doing things live again. Well, we're gonna use Y pipe, and we see that we're really close here. We're getting a lot better with our fitted values, and then finally we can bring down our metrics, which is R squared MSE and RMSE in this case, and we should be able to see that our model is slightly worse, actually. It's worse than the multivariate model. So what I'm looking at is that my R squared is 0.5, which is still right. That still uses Z. Pipe.fit Z. I think that's still right. And then, oh, it's not LM1 though. What's it called? Pipe. So my R squared has dropped to 0.25 and my RMSE has gone up to 494. So we're actually a little bit worse, but we can actually tune this a little bit. I think it's degrees equals 3. No, degree. Ooh, there we go. So what we've done here is that I've made this, by default, I think it's quadratic. So now we've gone up to n equals 3 in my polynomial features. And if we run this through, you'll see that we're better. We're down up to 0.7 and down to 300 for my plus or minus uncertainty. So that's pretty good. And you can keep fiddling with this. We can make this degrees equals 5. And now you can see that we're essentially perfect with our model, which is pretty cool. But again, I would warn that this probably is going to be an overfit model. All right, 2 o'clock. We're right on the money here. I'm going to do 15 minutes of our final activity, and then we can take questions. But big idea of this notebook and where I want us to get through in this live session. Data wrangling, data pre-processing. How important is it to do that data pre-processing to get good features for your model? And then second, what is a linear model? What's the history of it? Why do we start with linear models in our predictive modeling? Why don't we just jump straight into XGBoost and neural networks and deep learning, right? Hopefully you should understand a little bit of, I call it the complexity versus explainability trade-off. Where's my chat? Complexity versus explainability. Basically, as your models get more complex, right? As you start using neural networks and things, and even polynomial regression, the actual model itself becomes less explainable to share with non-technical stakeholders. You also see this as like the accuracy versus explainability trade-off. Typically, complicated models are more accurate, as we can see with my polynomial regression here. It's a more complicated model, it's a more complicated equation, but it's a better fit, right? It's more accurate. And you see that with neural networks too. As you do more complicated models like neural networks, they will be maybe more accurate or just as accurate as your linear models, but you've almost lost all explainability in how the algorithm is generating its prediction. So just something to kind of keep in mind here as we start working through that. All right, 10 to 15 minutes or bust. Let's go through our final keynote. The final project is actually a lot easier than some of these other ones, but let's get into it. This is going to be 5:10. And let me go ahead and launch that. We'll do it live. All right, so in 5:10, it's all the same problem, right? Given everything we know about data preparation, data pre-processing, generating and creating linear models, and then evaluating linear models and their performance, we want to drive that all home with a real data set. Housing sales in King County. I'll say if anyone knows where King County is, let me know. I may try and Google that real quick. King County, Washington State. There we go. It's probably not the one in Texas. I think that's probably the one in Washington State. So up in Seattle, we're going to be using this data set on housing prices up in Seattle. And what we want to do is we want to build a linear model, a multivariate linear regression, and then a polynomial regression, and kind of see how we can do on that. So let's restart kernel and get moving here. I'm pretty sure this one doesn't give you the answers either. Yeah, so you're supposed to do this one without the solutions. If you're curious, I've already done this on my GitHub, so you can always grab the right answers from my backup in over there. And we're still waiting for the kernel. Maybe it'll work. A lot of these, a fun fact, a lot of these kernels, this is actually a cloud computer being hosted and run somewhere. So when we like restart and kill our kernel, what it actually is doing is like restarting a VM or virtual machine that lives on the cloud somewhere, somehow. And then that's where we execute this code on. If you're familiar with services like AWS SageMaker, it's a very similar idea with what we're doing with these IBM Jupyter Lab notebooks. SageMaker is basically Amazon's Jupyter Notebook interface like this, where they, oh my goodness, I'll nuke my kernel again. Basically, SageMaker is the same idea, but all the cloud compute that you utilize to run your notebooks is obviously happening on a AWS managed virtual machine. Leaving you notebook. Yeah, so if you look at this one, right, you can see that like this kernel is active and idle, while this kernel is unknown. Maybe I can run it off this one. No. Womp womp. You've just been patient. I feel like if I just let it run for a minute, it would have just done it. No, I'll give that a second to run. I'll try and be patient this time. I work in the cloud every day. I know how long it takes to kill and restart VMs. Yeah, so what the new thing is for a lot of this workflow, so obviously I work for a company called Databricks, but IBM and AWS do similar things. We now introduced kind of an idea called like serverless compute, which basically is the idea that instead of having to reconnect and restart your virtual machines, We just have basically what's called a warm pool, basically computers that are always on and available that you can just connect to. And so it kind of eliminates some of that like kernel latency issues that we see with things like this. Hmm. If this doesn't work in another minute or two, we may need to pivot over. All right, this seems to, we'll go to a quick little backup here. I'm gonna go to Google Colab and just run that as a backup. So what I'm gonna do here is I'm just gonna open up my backup version of 5.10 just so you see what it looks like when we run it. And I'm gonna try and run it in Google Colab instead. Yeah, so same thing over here. We're gonna connect to a runtime. Same idea. This is gonna be a virtual machine in Google Cloud, and it must have a warm pool or something because that was super quick. I don't know why IBM Cloud is mad at me right now. Shut down all kernels. Watch this like click over as we start running it in Colab. I believe in you. I guess not. All right, so let's just start running this in Google Colab, and I already have the answers in this notebook anyway, so this should be pretty quick. All right, so let's kind of get into things. First, we're going to do is grab our data set, which I'm using the requests library to do that. And we should be able to see that over here. We should now hopefully have a file called housing CSV, which hopefully should show up here in a sec. There it is. So we have our CSV data that we've downloaded, and then we don't need to do that. Well, I guess it's fine. Oh my God. I guess we shouldn't do that. I don't know why Colab added that. Let's just read in the CSV over here. And we can look at df.head to see what our data looks like. So same kind of idea. We have this unnamed 0 column, and we have all these other features in our data set. We actually have 22 columns, which is pretty cool. If we run df.dtypes, we can see all of our different data types. Date is probably the wrong data type here, but all the rest look pretty good. We can also run, I'm getting discombobulated being in a different editor, df.info, and we can see same idea. Notice we're up to 21,000 rows. It looks like bedrooms has 13 null records. We still have that column we probably need to drop. And then all these other data types look good except for date. And looking at the dot head again, date is this weird timestamp. So we could probably do some engineering to fix that, but that already makes me sad that I have to do all that work. All right, so data wrangling, looks like there's a few things we need to do. First thing we're going to do is drop ID as well as the unnamed 0 column, as they are no longer needed in our data set. From there, we can look at our null values. It looks like bathrooms also had some null values. Yeah, bathrooms has 10 null values as well. So we have two columns with null values, and we're going to do some imputation. In our case here, we're going to impute the values. I'm going to call this mean bedrooms and mean bathrooms. Yeah, I'm trying to keep my variable names a little bit more descriptive. So it's actually interesting. I probably wouldn't do the mean here, and I'll tell you why after we do it. But if we actually run this imputation cell, we're replacing number of bedrooms with 3.372. And same thing with the bathrooms here, right? With 2.11. You're never going to have 3.3 bedrooms and 2.11 bathrooms. So I would probably do the median. And the reason why is because my median is going to be a solid integer. And now I have to do the same thing I have to rerun my cell again. Since we dropped those columns, I have to basically start from scratch, reread in the data frame, and then fill those in using the median. There you go. So you can see that my median number of bedrooms is 3.0 and my median number of bathrooms is 2.25. So maybe we can have like a half bath or a quarter bath. So I guess you can have a quarter of a bathroom. And now we should have no more null values in my data set. Let's do a little bit of exploratory data analysis to see where we have outliers or anything. We can see that again, we're biased, right? We have small samples. Houses with 3.5 floors, we don't have very many. Houses with 3 or higher, we don't have very many. We have 21,000 rows, if you remember. So the fact that we have like 620 out of 21,000, less than 3% of all of my houses have 3 or more stories. So that's going to be a small sample size if we get that impact, right? Um, and then same thing here, we're going to be looking at some box plots. Basically what I'm looking at is outliers. So what we're supposed to compare here is, do we think that houses with a waterfront view, are they more expensive? To me, it looks like, again, we just have a small sample size, but on average, this line right here is the median. We do have more expensive houses that are on the water than not on the water. But we can see we have all these outliers, right? So we just have some really expensive houses, regardless of if they're on the water or not. So I don't know how predictive that feature will be. And again, if we actually look at I'm doing too much live coding here, df.waterfront.value counts. If we actually look at the distribution, again, 163. So small sample size, right? 163 over 21,000 is like less than 1%. So I don't trust this at all. We don't have enough houses on the water to even have a confidence that they are actually more expensive. Fun fact, you can start if you're curious, you can look at like the SEM, which is the standard error of the mean, which basically tells you like, hey, given the number of rows in your data set, how confident are you kind of in this value? So, given the number of that we only have like 163 houses, how confident are you in that average price? It's gonna have a lot of uncertainty around it. Next, we can use this SNF, the Seaborn function called regression plot, which will basically give us our line of best fit on a nice little graph for us. You can actually make it like red, I think. Maybe. I wanted the line to be red. Oh well, I'll figure out how to do that later. But you can make the line a different color. And we're looking at square feet versus price. There does seem to be a pretty strong correlation here. The square footage of the house does dictate the price. We can prove that with the correlation. Square foot of the living area has the strongest correlation, and zip code has a slightly negative, but I would say that's basically zero. So interestingly, the year built is also a fairly low correlation. Perhaps if we bucketed that, like I mentioned earlier, into decades, it would have a stronger correlation to price. All right, so let's build a simple linear regression model. We're going to use longitude to predict the price, and we see that it doesn't mean anything. And again, this is expected because longitude has a very low correlation, so we would not expect to see anything there. If we use the square foot of the living space, you'll notice that we actually have a much higher R squared value here with 0.49. Oh, that's the next example. I should have read ahead. Yeah, if we use the square foot living space, you'll see that that goes up to 0.49. Next, we're going to do a multilinear regression. using a list of features here that have already been cleaned for us. We're going to use this multiple feature set, and we get a high score of 0.65, although not all of these features are created equal. For example, if I take out Waterfront, this is why I like data science. You can experiment and see like differences. You'll notice that without Waterfront, it's still basically the same. But maybe there was some impact in having Waterfront there because it did seem to increase my R squared by about 1.7. All right, next up, let's create our polynomial fit. By default, we're going to use degrees equals 2 for our polynomial. And the idea should be that with a polynomial pipeline with that exact same feature set, which is, yeah, x, we should see a slightly better fit, which we do, 0.75 versus 0.6, which means we're capturing some nonlinear effects. And if we actually add in our degree equals 3, it's even better, up to 0.81. But again, now we're kind of maybe going into overfitting territory. We can look at some evaluation metrics like cross-validation as well. So that's what we're doing here. We're splitting our data into training and testing sets. Again, we'll go more into this in week 7. We can use more complicated algorithms such as Ridge. Ridge is still a linear model, but it can send some of the coefficients down to approximately 0. Again, we'll go more in depth in regularization in week 7. This is just more of a like show you the art of the possible. And we can see here with my Ridge model, our testing and training set are very similar, which means we don't have overfitting, and they are both around 6.5. And then I was gonna say, yeah, now the last thing that I would do is do your polynomials and then fit your pipeline with the ridge on the polynomial set, which is exactly what it's doing. And we get that output of 0.70 and 0.74. Again, you can see how our overfitting is starting to come about here. Our training set is higher than our test set by a little bit of a lot. If I change my order, you're gonna see that overfitting continues to grow. Hopefully. Yeah, with a polynomial order of 3, we have a really good training score, but a really bad testing score, right? So that's overfitting for you. Our model is good on training data, but bad on unseen, not seen, not known testing data. And that's a risk you run into with these polynomial features, is that as you start jacking up the number of degrees, you run into that risk of overfitting. And I guess I'm going to bet as we go into degree 5, we're going to overfit even worse, hopefully. You can see it's also taking longer to run here, just because of the more complexity in our model. I can't even go for it. Hopefully I haven't killed all my virtual machines. Oh no, it's mad at me. Uh-oh. Stop. Yes, restart. All right, I was going to restart our runtime and run all. I'm going to jack this back down to 3. But that's the end here. So big idea from this week. Things you should know: the importance of data wrangling, feature engineering, data preprocessing. So that'll be imputation, data types, encoding your categories, standardization, normalization, all of that good stuff. Then you should know a little bit of the history of linear models and why linear models. You should then be able to talk about linear regression, multivariate regression, and polynomial regression, as well as evaluation metrics such as R squared, MSE, and overfitting. Again, we're going to go deeper into this when we have 2 more weeks on machine learning. We'll spend more of that time on classification models, tree-based models, deep learning models, but this foundation will kind of take you through that. If your more complicated algorithms don't beat your linear models, then what are you doing, right? Like, why are you using them at all? But it's a good week though. Again, go slow with it. If you have questions, kind of bring it back into the forums and the discussions. Try and participate in the discussions if you can for this week. Next week is a bit of a breath of fresh air. We're going to be just doing visualizations, pie charts, bar charts, line charts, all that good stuff. So it's going to be a little bit of a break from this kind of hardcore modeling week that we're doing. Again, we're kind of throwing a lot at you in week 5 with data preprocessing and modeling. So I totally get it if it's overwhelming. Just go slow and know we're going to reiterate on these ideas in week 7 and 8 as well. All right, I'll stick around here for another 5-10 minutes. And if you have questions or want to stick around online, you're more than welcome to. Otherwise, thanks so much for joining, George, Arfa, and we'll see you on the other side. See you next week, I guess.
Thank you, Alex. Thank you, Karen. Great presentation, as always.
Yeah, sorry my kernel kind of died on the. If this ever happens to you as well, my advice is either just leave it, come back to it, close out, come back in an hour, or just pivot over to Colab. So yeah, Colab and my GitHub is always a good backup option.
Perfect. I'm still catching up from my travels, so I'm still on module 4. So
Yep, totally fine. And again, same with that module 4. I recommend is click throughing the click through labs and then really focusing on 4, 11, 13, and 16 in the notebooks.
Sounds good. Thank you.
All right. Thanks all. I'm gonna stop the recording here. And again, like I said, I'll be online for another few minutes if needed.
Sure. Thank you.
Thanks everyone.